second part of laboratory experiment. Second part is we have to design for G P of S equal to e power minus 1.346 upon 3s plus 1. 1.346 sampling period. Let us assume that t equal to 1. Sampling period equal to 1. The dead time is not equal to, not integral multiple of. Dead time is not integral multiple of sampling period. Not integral multiple of sampling period. That's why we have to use modified Z transform to find HGP of Z. What is HGP of S? HGP of S equal to e power HGP of Z equal to 1 minus e power minus S upon S. That is for H. E power minus 1.346 S upon 3s plus 1. That is equal to, this can be separated in two parts. 1 minus e power minus S upon S. E power minus S, e power minus 0.346 S upon 3s plus 1. Whatever integral multiple of sampling period can be taken outside in terms of Z transform. That's why HGP of Z equal to 1 minus Z power minus 1 for this part. For this part, Z power minus 1. Z power minus 1. The remaining part, modified Z transform of e power minus 0.346 S upon S multiplied by 3s plus 1. If you find the modified Z transform for this 0.0876 Z power minus 3 plus 0.1959 Z power minus 2 upon 1 minus 0.7165 Z power minus 1. Modified Z transform of e power minus theta S upon S multiplied by tau S plus 1 equal to Z power minus 1, 1 by Z, 1 by 1 minus Z power minus 1 minus e power minus m by tau divided by 1 minus e power minus 1 by tau e power minus m by theta Z power minus 1. Where m equal to 1 minus theta by tau. In this case, 1 minus theta equal to 0.346. 0.346. That is equal to 0.66. M equal to. If you substitute, you will get this result. You find yourself. So HGP of Z we got. But the numerator, if you add these two together, you are not getting 1. If you add these two together, you are not getting 1. What is the sum of these two? 0.0876, 0.1959. If you add these two, .2835, 0.2835. Divide the numerator and denominator by 0.2835. Now you will get the coefficients such a way that if you add these two, you will get 1. If you add 0.0876 divided by 0.2835, you will get 0.3089 Z power minus 3 plus 0.6910 z power minus 2 upon 1 divided by 0.2835 is 3.5273 minus 2.5273 z power minus 1. So this is HGP of Z. HGP of Z. We got two terms. If you add the two terms, it's equal to 1. Therefore, the numerator is P of Z. Denominator is Q of Z. Now we can find the controller D of Z. What is the controller D of Z? The controller D of Z equal to Q of Z upon 1 minus P of Z. 1 minus P of Z. When we can call it as P of Z, the sum of coefficient must be equal to 1. Yes. Here, now if you add these two, we are getting 0.9999. So the sum of coefficients, if you check for P of Z, 0.3089 plus 0.6910, if you add 9999 point, that is approximately equal to 1. Therefore, the numerator can be called as P of Z. Therefore, D of Z equal to Q of Z, that is 3.5273 minus 2.5273 Z power minus 1. That is Q of Z divided by 1 minus P of Z. 0.3089 Z power minus 3 minus plus 0.6910. Why minus? Because as per formula, 1 minus P of Z minus 0.6910 Z power minus 1. 0.39 Z power minus 2. Yes, we got D of Z. We got D of Z. 0.35273 minus 2.5273 Z power minus 1 upon 1 minus 0.3089 Z power minus 3 minus 0.6910 Z power minus 2. We got, if you convert this into positive powers, you will get D of Z equal to 3. Multiply the numerator denominator by Z power 2. Z power, highest power is Z power minus 3. Multiply the numerator denominator by Z power 3, you will get 3.5273 Z cube minus 2.5273 Z square upon Z cube minus 0.6910 Z minus 0.3089 constant term. Here, one missing term is there, that is coefficient of Z square is 0. So we have to enter the and check in the MATLAB. The transfer function is 1 upon 3s plus 1. The dead time we assumed is transportation delay 1.346. So the controller is 3.5273 Z cube minus 2.5273 Z square. Z term, coefficient of Z term is 0 and coefficient of constant term is 0. The denominator, coefficient of Z cube is 1, Z square is 0, then coefficient of Z term is minus 0.6910 and constant term is 0.3089. So we entered the controller. Let us check. Yes. What is the assumption we made? What is the dead time? 1.4346. That is greater than one sampling period. That's why there is a delay. In the first order response, there is no delay. It starts from 0. Here, there is a delay. After that, it increases slant line. Next sampling period, if you see some in-between value, you will get. From third sampling onwards, it is 1. So we got the ideal response. We got the ideal response at the 40th sampling period. If you see here at the 40th sampling period, we gave a disturbance. At 40th sampling period, we gave a disturbance of unit disturbance is given. For that also we got the response. Here the IAE is 4.6 and ISE is 2.7. We are not going to compare with any controller. That's why if you can compare with the conventional PID controller, sometimes in the lab it may be asked like that. In that case, you have to compare. Otherwise, here no need. Anyhow, we found IAE and ISE. So we got the response as we assumed. That is important. What is the assumption we made? There is no overshoot. The response is like first order response. Yes, we got like first order response after a dead time. Now let us design the controller for fourth order process. Fourth order process. Fourth order process. What is that fourth order process? For that we have to design 1 by s plus 1 to the power 4. That is can be approximated as e power minus 1.436 upon 3s plus 1. It is approximated as first order plus dead time process. So if you find HGP of Z, you will get the same. That's why the controller will be the as we got for the previous case, because that is the mathematical model for the given fourth order process. So we can enter the same controller for this fourth order process also, and we will check for that fourth order process. But here it is approximate model. That's why you cannot expect that ideal response. It is approximate. That is the difference. Here, if you enter those parameters here, yes, we entered the controller here. Yes, we entered the same controller because it is assumed that the fourth order is approximated to first order plus dead time, and we entered fourth order process instead of first order plus dead time. We entered the actual process. This is happened in practice. In practice, process will be actual, but we are modeling it as first order plus dead time. So that's why this is more important. So if you find the response for this, we are giving disturbance at the 40th sampling period, and we are giving initially we are giving a step change, a unit step change. For that, the response is yes, but it is not ideal case, because we are approximating the given fourth order model as a first order plus dead time. That's why oscillation is there. So it is not ideal case. That is the difference between the previous one and this. There, the controller is for which it is designed. That's why we got ideal response. But here it is not so. We approximated the fourth order process as first order plus dead time. That's why overshoot is there, oscillation is there. But it controls. But you can compare this with the response of PID controller. Definitely, this will give better response than PID controller. That you can see in the lab.